Good day. In this lecture, we will discuss crystal structure, focusing on how atoms are arranged in solids and how this affects material properties. By the end of this lecture, you should be able to identify different crystal systems and describe their structural characteristics. Solids are classified into two types. We have crystalline solids, which are ordered, and amorphous solids, which lack order. This distinction is fundamental in material science. In crystalline solids, particles are arranged in regular repeating pattern, while in amorphous solids, there is no long-range order, leading to irregular structure. Crystalline solids have definite shapes, sharp melting points, and directional properties. Amorphous solids melt over a range and have uniform properties in all directions. This difference is described as anisotropic versus isotropic behavior. An example of crystalline solid is quartz, and an example of amorphous solid is glass. Both contain similar composition, but they differ in structure and properties. Each point in the lattice system represents an atom, ion, or molecule. These are called lattice points, and they define the geometry of the crystal. We have a term called crystalline lattice, and that is the arrangement of the particles in a crystalline solid. We also have crystal lattice or lattice structure, which is the regular three-dimensional arrangements of points in space. The unit cell is the basic repeating structural unit of a crystalline solid, and each sphere is called a lattice point. These lattice points represents an atom, ion, or molecule in the lattice system. Repeating unit cells forms the lattice structure of your crystalline solid. The unit cell is defined by the edge lengths and the angle between edges. These parameters determine the type of the crystal system. There are 7 crystal systems based on different combinations of lengths and angles. These define the possible geometric arrangement of the crystals. Angle alpha is defined by edges B and C, angle beta by edges A and C, and angle gamma by edges A and B. For simple cubic, the angle alpha, beta, and gamma has an angle of 90 degrees. The same thing is true for tetragonal and orthorhombic systems. For rhombohedral systems, angle alpha and angle beta is not equal to 90 degrees. The same thing is true for angle gamma. For monoclinic systems, the angle gamma is not equal to angle alpha. However, angle alpha and angle beta is equal to 90 degrees. For triclinic system, none of the angle is equal to each other and none of them is equal to 90 degrees. For hexagonal systems, both angle alpha and angle beta has 90 degrees and angle gamma has 120 degrees. The cubic system has 3 main types: the simple cubic system, the body-centered cubic system, and the face-centered cubic system. This differs in how atoms are arranged inside the unit cells. In simple cubic, atoms are only at the corners. For body-centered cubic, it has an additional atom in the center. And for face-centered cubic, it has atoms at the centers of each face. When counting atoms, corner atoms are shared by 8 unit cells, face atoms are shared by 2, and edge atoms are shared by 4. This determines the number of atoms per unit cell. This sharing concept ensures accurate calculations of atoms in a crystal. It is also essential for determining the density and the packing of the crystal system. The coordination number is the number of nearest neighbors surrounding an atom. It indicates how tightly atoms are packed. The larger the coordination number, the closer the atoms are to one another. A coordination number 4 indicates relatively loose packing. Atoms are not maximally surrounded. In simple cubic structures, the coordination number is 6. Each atom touches 6 neighboring atoms. In body-centered cubic structures, the coordination number is 8, and this represents more efficient packing than simple cubic. In face-centered cubic or cubic close-packed structures, the coordination number is 12. This represents very efficient packing and high stability. Hexagonal close-packed structure also have a coordination number of 12. They achieve similar packing efficiency through different geometry. Examples of HCP are magnesium, titanium, and zinc. For FCC, that would be aluminum, nickel, and silver. These structures influence mechanical and electrical properties. Voids or holes are empty spaces in the lattice, and these are important because they allow movement of electrons or ions, and they influence properties like conductivity and diffusion.